Good afternoon. Welcome back to CHEM 400. So exciting. I don't know, we're at an all-time high for the number of people who have had their homework checked ahead of time and get 10 out of 10s on it because they've had all their problems checked ahead of time. What's happening is I'm checking them in office hours, and then as time allows, checking them in labs as well. And those of you who have discussion this afternoon, and those of you who had it on Monday, I check them in discussion as well, time allowed. And so what that looks like in lab is, if there's a lab question, they go to the front of the line. And if in discussion there's a discussion question, front of the line. Otherwise, let's get all this homework checked ahead of time. As early as you can do it, I'm happy to grade it. Right? It doesn't always happen, but I actually have all my answer keys for the entire semester done. So, one announcement, E1, that's exam 1, that's next Wednesday, 1 week from today. That will take the entire time. It will be based on homeworks 1 through 4, so you've done homeworks 1 through 3 already, and I'll post the key later today for homework 3. You will be working blind for homework 4 because you'll be working right up until it's due, but as I've mentioned, you have plenty of options to get your homework checked ahead of time. A number of people, and I did my best. I think I missed responding to one email, but a number of people had emails, and I responded even over the weekend. So, 2, they sent me a picture of their work on the homework, and then I commented right or wrong. Homeworks 1 through 4 are on chapters 1 through 4. Now, we emphasized a lot on chapter 4, so that's going to be the biggest part. Chapter 3, the biggest thing we did was, chapter 3 was limiting reactant and empirical formula and combustion analysis problems. So anyway, I went ahead and I got an old exam from the People's Guide, and as I look through it, it says multiple choice / fill in the blank, 4 points, unless otherwise noted. You should expect about a page of multiple choice or fill in the blank. Then you should expect 24 points of nomenclature. The nomenclature is what's covered is detailed on the nomenclature handout in your People's Guide. But it'll look very similar to this, and so if you know how to name these compounds, then you're in relatively good shape. And then there's what I call the free response section. You are free to respond. And I suggest that you don't leave any of these blank. It is impossible to get any credit if it's blank. You may not get any credit, but I do my best to award partial credit for partially correct work. That means at the bottom of page 2, page 3, page 4, page 5. Yeah, page 5 is the end of this one. Short answer questions. You'll notice that one of the questions has these little atoms on it. We've seen those a couple times on the homework before. And hopefully what you will find when you look at this exam is, well, hopefully you'll look at it and be like, I've seen this on the homework and I know how to do it. But even if you don't know how to do it, hopefully you say, I've seen this on the homework already. And I can check and figure it out from that. And then always check with me. Alicia?
I can see that on our website.
This is not on the website. This is in the People's Guide. So check your People's Guide. Yeah, these are the yellow, what are called canary yellow pages. Your exam, if I get my act together, will probably be on goldenrod paper, which is another color of yellow. So the format will be the same. The questions, of course, will be different. Let's see. Which, mix up. Yeah.
Key for this?
No, no key for this. You know why there's no key for this? Because nobody's made me a key. The keys for the other practice exams, which they are there, students made for me. So if anybody wants to make me a key or draft a key that I comment on, I would be willing to work with that. Otherwise, good luck. Talk to me. I'll answer all your questions about these, whether they're right or wrong. That's just always how I've done it. So last fall, when I taught Chem 400, a student made the key, and then there was a couple small fixes that I fixed, and then I posted it. So I'm open to that option, but I'm not open to making my own key or the key. So anyway, talk to me if you want to do that. making the key. Great practice for the exam too, and your students really appreciate it. Your fellow students. Good. Any other questions? Okay. When you look in the People's Guide, you'll see that the page after the exam is actually a take-home portion. I reserve the right to have a take-home portion to your exam, and until I make it up, I won't know, and I haven't made up your exam yet. I'll probably make it up over the weekend. Okay? All right, then. Well, where were we? We were somewhere around here. There we go. That's where we were. Where were we? We were talking about, yes, Brenna.
Just real quick, we don't need a Scantron for the testing.
You do not need a Scantron. The one page of multiple choice I will grade right on your exam. You will get your exams back after I grade them. So, yeah. Any other questions? Well, we were working our way through chapter 4. We were up to the ion product of water. And I should say, actually, we're not working our way through chapter 4 anymore. This is a section that is from chapter 15. It is in the Chem 400 curriculum, and it is on your exam. And this is all the stuff that's here is the stuff that you need to know. You can look at chapter 15, and if you've been playing along at home and you've been reading the textbook, the way my class typically runs is my lecture notes are pretty inclusive. Meaning, if you know how to do everything in the lecture notes, you're in good shape for the exam. If you don't understand something, the textbook is, I think, the best textbook there is for looking over the material and getting another perspective. Having said that, if you like Khan Academy, if you have other sources, right, learn as best as you can. Be as efficient as possible. So, all right. So this portion is in the lecture notes. It is in, I think it's chapter 15. The ion product of water, that's the subject. Oh, yeah. First statement I want to make is that the product of the hydrogen ion and hydroxide ion concentrations is always the same number. The number is called the ion product constant of water. The ion product's constant of water and has the symbol Kw, where the W is a subscript. And what will happen is when you get to Chemistry 401, you'll see, and this is capital K. You'll see lots of capital Ks. They are what's called equilibrium constants, and this is about the only one we need for Chem 400. Anyway, so do you have to know this terminology? No, but we will be using it, and so that's sort of background in preparation for Chemistry 401. Kw actually has an equation associated with it. It just says that Kw equals the concentration of hydrogen ion times the concentration of hydroxide ion, where these square brackets mean whatever is in them, it is the concentration of that thing. So this symbol means concentration of A. In molarity, and that's capital M, and I'll still write it out. And from now on, well, with a couple of exceptions, one of which is you can be asked to do concentration units in parts per million or parts per billion, that's true, but almost everything else is molarity. Now, I cannot believe we've gotten this far without me saying this in lecture. I heart units. And so this will be my advertisement that every number on your exam, think about what the units are when you write it. The units are never more than 2 points per particular number that I'm looking for. Sometimes they're 1, sometimes they're half, and sometimes they're 2, but those are actually not that hard points to get. And you're always sad when you don't get them. Or I'm always sad when I subtract them. But anyway, so that's my advertisement for units. I love units. I heart them. And I thought of that because of molarity. Anything that has a molarity also has like molarity sodium chloride, molarity calcium ions, molarity of whatever it is. Okay. This is an equation that's not actually done. It equals 1.0 times 10 to the minus 14. And we'll use this a couple times. Now what this means is that as the concentration of H plus increases, the concentration of hydroxide must decrease so the product stays constant. One way to show that is if I rearrange this equation and solve for the concentration of hydroxide by putting the concentration of hydrogen on the other side. I get that 1.0 times 10 to the minus 14 divided by the concentration of H plus is equal to the hydroxide ion concentration. As one gets larger, while this stays the same, the hydroxide ion must get smaller. Concentration must. Any questions about that? This isn't always, and when I say that, it is always true in water. And in Chemistry 400, and pretty much Chemistry 401 as well, we're always in water. Water is the solvent. We'll have aqueous phases, we'll have liquid phases of water. We have so much water in Chem 400, we're practically swimming in it. Now, so this underlies a lot of things we do. This is the ion product. Now let's get back to what we were doing. We were talking about acidic and basic solutions. And all aqueous solutions contain both hydrogen and hydroxide ions. Neutral solutions have equal concentrations of them. Now, we haven't gotten the pH. We're building up to pH right now. What's the pH of a neutral solution? Does anybody? 7. 7.00, true. Now, does anybody know what that means for the concentration of H plus? Well, let's I don't know. Maybe you're thinking about it, but let's keep going here. I'm going to come back and I'm going to write out this equation. Just the concentrations equal this number. Concentration of hydrogen times concentration of hydroxide equals 1.0 times 10 to the minus 14. Truly, the definition of a neutral solution is that these two are equal. Neutral solution, concentration of H plus equals concentration of hydroxide. And it's at this point that I will apologize to you. I've made one mistake. It's a mistake by omission, but I want to come back to this one. This number is at 25 degrees Celsius. Sorry, I forgot to add that.
Room temperature?
Approximately room temperature. I'd say it might be 21 in here, maybe 22, so very close to room temperature. All right. So next what I want to do is if these two are equal to each other, question, Bodhi?
Why 25 degrees Celsius? I've seen that a lot in chemistry, and I want to know what's the significance of it.
Good question. Why 25 degrees Celsius? Well, so we don't talk about it a lot in chemistry 400, but the temperature comes up a lot more in chemistry 401. So chemists needed a reference temperature, and chemists picked 25 degrees. And why 25? Because it's near room temperature. It's actually generally a little above room temperature, so you actually have to work to get it there. And then they just said 25 degrees, we're going to define everything according to that. And so that if I'm doing chemistry at UC Davis, or if I'm doing chemistry in Costa Rica, we can all say, let's agree on 25 degrees as a reference point. Okay. Now, at some point, when we get to chapter 5, the people who work with gases said, let's choose 0 degrees Celsius. And so when we talk about gases, that'll be our reference point, but for gases only. Everything else is 25. And it's sort of like, it gives you a common language, right? In the same way that those of you who play music, the notes are all, they could be any letters. Why not call them A, B, C, D, E, F, G? I think those are most of the notes, aren't they? I mean, they're sharps and flats. But it's like giving us a common language.
Does that mean our labs should all be at 25 degrees Celsius when we're doing labs?
Good question. Does that mean our labs should all be at 25 degrees Celsius? Yeah.
Are they?
No. But they're close enough. And what we'll see is that there's a standard temperature, there's a standard pressure. That pressure is 1 bar, which is very close to 1 atmosphere, which is, again, atmospheric conditions. So are we doing all of our experiments at 1 atmosphere or 1 bar? No, but we're doing it very close.
Okay.
So, and when we get to chapter 6, we'll say the difference between 25 degrees and what we're doing is not significant. Or close enough.
I know you're working up to it, but if I have a glass of water and I put a significant amount of acid into it, it will become base and vice versa.
Good question. So your question is, okay, I just said that they always have this. You're saying if you put acid in water, will it become basic?
Yeah.
And the short answer is no. If you put acid in, you're going to get more H pluses than hydroxides, which means it will still be acidic. What I'm saying right now is no matter how many H pluses you put in there, there's still a very small amount of hydroxides. Okay? And that is always true. If you have 12 molar HCl, you can calculate the concentration of hydroxide in it. And it will be, well, the more H pluses we have, the fewer we will have, but we will always have some. Does that answer your question?
So the opposite is true.
If the more hydroxides you add, the more basic it becomes, but there's always H pluses in it. And we're about to calculate that to show.
I'm talking about the changes that occur once I add.
They're inversely proportional. But one's never infinity, so the other one's never 0. I hang in there. I think you're going to see. You have another question? Yeah.
Never mind. I mean, like, never mind. This is a dumb question.
I bet it's not, but hang on and let's see if we tackle it. All right, so the next thing we're going to do is that the definition of a neutral solution is these two. Were you going to ask about different temperatures?
No, I was going to ask about, I mean, there'll always be like a decreased amount of H plus to OH, but has someone ever got it to 1? Like there's 1 concentration of either one? Like 1 atom.
It's a fair question. Here's my unfair answer. See where it says always here?
Mm-hmm.
I meant it, right? There's no way to make this so big either of these, that the other one goes to 0.
I'd say the
And you
one.
can't
though.
divide by 0.
Oh, can I make this one
Can you
1?
make it like
Or how about we make this one 1?
So high that there's only one atom of H plus.
Oh, one atom.
Yeah.
I was going to say, since these are molarities, I could make this 1 molar. If I make this 1 molar, 1 molarity, what's this mathematically? It's just going to be, if this is this divided by 1, then this is 1.0 times 10 to the minus 14. A very small number. But even minus 14 is much bigger. So if you did this moles per liter and you multiply it times that 6.02 times 10 to the 23rd, I still get 10 to the plus 9th atoms, or in this case, ions.
Okay.
Right? Atoms are so tiny that you, no matter how small you get in a concentration, you've still got a bunch of them. Right? I mean, that's why it was so hard to figure out that atoms existed, because you always had so many.
So is the number the 6.022 times 10 to the negative 23? Is that correct? Or is it
Positive
just-
23rd, right?
Yeah. Or is it?
Is that correct? Yes.
Or is it just like a guess? It's like correct. Like that's how many atoms.
This is a great question. Did you know they just redefined the mole?
What?
Yeah. They changed its reference state. Because the mole is actually just, it's like 6.022, and then they have a whole bunch of other digits. And then way out here somewhere, there's error root. And so it's a determined quantity. And it's defined as the number of atoms. At least this was the old definition. In 12.0000 grams of carbon-12. But even that is a relative number. So it's interesting. I mean, I think there are lots of questions there that are interesting, but it is true that there is a finite resolution to this, or a finite accuracy.
But we don't know what it is.
We do know what it is. I just forget the rest of the digits right now. Yeah, and that there could be, there's like either 3 or 4 or 5. Like it stops eventually because of the limit of how accurately you can determine it.
So is it the amount of atoms in carbon-12, right? And so it's actually the amount of atoms in carbon-12, but what about a different element? Is it actually that, or we just...
Like 1 gram.
So then we say
Oh wait, no.
this number of atoms of anything else is how we figure out those numbers on the periodic table.
Okay.
So when you see 12.011, that's because there's some carbon-12 and some carbon-13.
Okay. Got it.
Yeah. Any other questions? If not,
My question earlier was if I did increasingly, so if I significantly increase the acidity by adding, maybe that was the wrong way to do it, then the base will increase.
if I increase acidity, which is represented by H+,
Yeah.
I decrease the amount of basic
Oh, yeah.
mass. Yeah. And actually, this brings up a good point, which is everything you know about acids and bases is still correct, right? If you think it's an acid, it's still an acid. We're going to layer some more theory on top of it and allow us to learn more about acids and bases. At least that's the goal. But if you like don't get stuck in some of these things like H plus is still what we think of as acids. OH minus will still be what we get when we talk about bases. We're going to add some things to it, but all that's already true. I would say we're peeling back the layers of the chemistry onion to learn more details about it. Okay? And what happens in Chemistry 401, we peel more layers back, because in Chemistry 401, you deal only, pretty much, with weak acids. And here in Chemistry 400, it's almost all strong acids. Interesting. Equals x, right? These two are equal. I'm going to say they're equal to x. That turns this equation into x times x equals 1.0 times 10 to the minus 14. Which is really just x squared, one equation, one unknown, solve for x. 1.0 times 10 to the minus 7. That does have units of molarity. And that is the concentration of H plus for a neutral solution. It is also the concentration of hydroxide for a neutral solution. Because the definition of a neutral solution is that they are equal. Now, we'll do some calculations around these. We will shortly show that if we take the negative log of this to get pH, we get 7. And that's where the 7 criterion comes from. Acidic solutions have larger hydrogen ion concentration than hydroxide. Basic solutions have more hydroxide than H+. I don't think there's anything else to write. So we'll keep going. pH is a logarithmic scale. That's what it says there. I'm going to write down the equation for pH in a second. Perhaps you already know it. Those of you at discussion on Monday, the 2-hour portion, definitely know it because we did it a lot. pH equals minus log log the concentration of H+. Now we're going to add another one that's going to come up, and it's actually going to be rearranging this equation to solve for the concentration of H+. If I want to clear a logarithm from this equation, what do I have to do to it? I have to do the 10 to the of both sides, okay? So I'm going to do it 10 to the pH. And mathematically speaking, as long as you do the same thing to each side, it stays equal, okay? I'm going to do one other thing. I should have done this first. I'm going to multiply through by minus 1. That's going to move the minus sign over there. So that's still a true statement. 10 to the something and log of something cancel each other out. And on the left-hand side, I get 10 to the minus pH. Question, Alicia?
What does pH stand for?
Thank you. It stands for the power of hydrogen. Where by power, we don't mean it in the Marvel Universe sense. We mean in the exponent sense. And in fact, it's really originally a French term, which was puissance, which means power in French. Yes, that's where it comes from. Good.
That's why one is lowercase, the other one is uppercase.
Yes, I think so. So the H is actually hydrogen, right? Power of hydrogen. And I mean, that's what it is. I don't know if this equation's on your conversion and equation sheet. If it is not, you should memorize it, because as you'll see on homework 4, you use it like 10 times. And hopefully you commit it to memory that way, but just in case, you do need to know it. The pH equation, many of you may know it. Memorize that as well, because there will be, and you can check the old exam, conversions from concentration of H plus to pH, and possibly, and pH to concentration of H plus. Any other questions about this? If not, I think we're supposed to do something else now. Good. See this equation in black? I'm going to write it again over here. And I'm going to do something similar. Like so, this time I took 10 to the both sides. For this equation, I'm going to take the negative log of both sides. And I'll do this in red. And I'll do it in blue. So I'm taking the negative log of the whole equation. If I do that, I get the negative log of the concentration of H plus. These two things being multiplied together, their logarithms are added. That's a logarithm math rule. So plus the negative log of hydroxide. Logarithms are added, or in this case subtracted, or they're added when they're multiplied. When I take the negative log of this, it's just a negative log of a number. Does anybody know the negative log of 1.0 times 10 to the minus 14? 14? It is just 14. And I'm going to put 14.00. And it turns out, as we'll talk about in a minute, the decimal places are sig figs, and I've got 2 sig figs right now. What is this? That is pH. Any ideas what this we might call this, Bodie?
POH.
That is pOH.
What does that stand for?
The power of hydroxide. And this equation will help you solve problems. Certainly, we use this in discussion this week, as you will see, or as you have seen. So this is another equation, and it all comes back. This equation, these equations, they all come back to this. So this always that I said underlies a lot of things that we're doing when we talk about pH. Any questions about that? All right. We've said this a couple times. It's worth saying again, especially since it's on my handout here. More H plus equals less hydroxide, but both are always present. Good. Here's a table of some common pH values. Gastric juice for the human stomach between pH of 1 and 3. Does anybody know the acid, the primary acid that's in your stomach?
Hydrochloric acid?
Hydrochloric acid. Awesome, by the way, that somehow we've developed to have strong acid that can digest anything, really, almost anything, in our stomachs. Whereas, do not drink hydrochloric acid, because it will react with your entire esophagus and kill you. And yet we have HCl in our stomachs. All right. We got a bunch of foods. Foods tend to be acidic. Not all foods, however. pH of human blood, 7.3 to 7.4. Household ammonia. Cleaning solutions, more often than not, they're bases. They react with the acids in food to react them away. Let's take a moment for ourselves. This moment involves sig figs and pH. the summary is that since almost all concentrations will have 2 sig figs for our, then you will have 2 decimal places on all your pHs. We said that on Monday. I'll say it again this afternoon. The exponent, which tells us where the decimal place is related to the whole number and is there and not significant. So 2 decimal places, please. Yes. Does it say that up here? If not, oh, the sig figs are the digits after the decimal point in the log. True. In this class, all pH values have 2 decimal places. Which is equivalent to saying that all pH values have 2 sig figs. I'm not sure why I put a blank here in my notes. I just want you to say the meaning of pH or more about pH. The lower the pH, the more acidic the solution. The higher the pH, the more basic the solution, and normal range of pH is 0 to 14. And so here's our pH scale, nicely illustrated from 0 to 14. 7 is neutral. Anything below that is going to be acidic. When you have a pH of 0, or let's do 1. When you have a pH of 1, I will write 1.00. That means you have a concentration of H plus of 10 to the minus 1. Those are units of molarity. All units involving pH will be molarity. When you have a pH of 4, a change of 3 numbers your concentration of H plus is 10 to the minus 4. Here we have a change of 3.00. Here we have a decrease of 1,000 times in the concentration of H plus. That's what a logarithmic relationship does. And if the pH changes by 1, the concentration of H plus changes by 10 times. Okay? And what you will more than likely see when you look over the old exams is there's often a question about this. The pH increases by 1. 2 questions I can ask. 1, does the concentration of H plus increase, decrease, or stay the same as it goes from, say, 1 to 2? And you would say that the concentration of H plus decreases. As we go from 1 to 2, we could also say, how much does the concentration of H plus change? And you would say it decreases by a factor of 10, or decreases 10 times. Any questions about that?
Why does it say normal range?
Good question. Why does it say normal range of pH is 0 to 14? Well, pH is generally applicable to biological systems. And for that reason, pHs are generally between 0 and 14. If you have 12 molar HCl, or let's do 10 molar. And you take the negative log of 10, because that's the concentration, you will get a pH of -1. And so it is possible to have pH values outside of that range. However, I will tell you this right now. On your exams and on all questions in Chem 400, the pH values will only, the answers will only have a range between 0 and 14.
It'll never be 14.1.
It'll never be 14.1. It could be, like you could get a situation where that could be true, but that's not where pH is usually used, and so you won't see it in this class. If you're using 10 molar HCl, you are not studying anything human. About the only thing you could do with a human in 10 molar HCl is dissolve the human. And that's an entirely different set of experiments. Does that answer your question? Could you dissolve? You can definitely dissolve a lot of parts of a human with 10 molar. I don't know about all of them. Anybody ever seen that show Breaking Bad? What did they use to dissolve the human? Do you remember? HF, hydrofluoric acid. Turns out fluorine, even though HF is a weak acid, fluorine has some really interesting properties. Side note, by the way, HF, very important industrial chemical for making computers. And when they use it, it is a serious safety issue. So, but we like computers, so we use it.
A lot of that was in the airborne at 9/11 site.
Yeah, well, making computers, like if you work for Intel, like I was gonna, before I became a teacher, I was thinking I might try and get a job at Intel. Thankfully, I'm here. But they use a lot of HF, they use a lot of chemicals. There's a lot of chemicals that go into the making of each of those computer chips. Did you hear what I said about the relationships here between pH and concentration? Because those do often show up on exam 1. And they should show up on your homework as well. They will. Okay. Finally, we get to calculate some pH values. We're now ready. We've gone through all the theory. Might be a bit of a letdown. I don't know. What is the pH of a 0.115 molar solution of HCl? Is HCl a strong or weak acid? It is a strong acid. What do we know about HCl? Does it break up? What percentage of ions does it break up into?
100%.
100%. So when I have 0.115 molar solution of HCl, what is my concentration of H+? 0.115 molar. Because it broke up. We also have 0.115 molarity chloride ions, not that anybody cares. Because one of the things you have to know is I will give you this on the exam. You have to make the jump to finding the H+, and then use the pH equation to find the pH. There's the pH equation. Good question. Will you have to do that for weak acids? Short answer, no. Long answer, weak acids break up in a much more complicated way, where all we said was that it was less than 5%. So no, we won't. Chemistry 401, yes. And that's what you spend a lot of time doing. So. Plug it in, chug towards your answer, 0.94. Is it between 0 and 14? Yes, good, because all my pH values will be between 0 and 14. That is true. A moment for ourselves. We have our exam coming up. If you get a pH of 57, go back on the exam set. Go back and think about what happened now. Who knows what's going to happen on this exam, right? But one thing that will not happen is the pH will not be 57 or minus 57. It will always be between 0 and 14. Now let's do sodium hydroxide. Same concentration. This time it's sodium hydroxide. Sodium hydroxide is one of our strong bases. That means that our concentration of hydroxide is 0.115 molar. Now, there's a couple different ways to solve this problem. One of them is to go back to our new friend, soon to become our old friend of this equation. We have our hydroxide ion concentration. We can rearrange to solve for H+, and then go back to our pH equation. That will always work, and that will always get you the correct answer. The other way to do it what is the other way to do it? Oh, sorry. That's why I was having so much trouble. It's based on the concentration of hydroxide. You can find the POH. And from the POH, you can find the pH. Either of those ways will work. The important thing is you know that if it's a basic solution, the pH has to be above 7. Are you with me on that? Basic pHs are pHs greater than 7. When you do this, you will find that the pH is 13.06. However you do it. And I guess I should fill this in too. So either way, it's a two-step process. You just have to figure out which way you like doing it the most. And different students do it different ways. Any questions about these? Yes?
So our final answer does not have a unit, right?
Your final answer for pHs does not have a unit. It's very distressing to me, but it's also true. And pHs are one of the few things that don't have units in this class. Because they're logarithmic. There's actually a more complicated answer, but the short answer is they don't have units. Okay. Any other questions? Good. Okay, now probably the end of chapter example. Ties a lot of different things together. This is going to be an acid-base neutralization reaction with a limiting reactant. Let's suppose 11.51 milliliters of 0.100 molar sodium hydroxide is added to 25 milliliters of 0.151 molar hydrochloric acid. What is the pH? Now, if this were your exam, there would be one other piece of information here. It would be the balanced overall reaction for this process. Let me put that up here. Hydrochloric acid plus sodium hydroxide goes to H2O, water. Plus, in this case, sodium chloride. So you'd have that. Now, do we have enough information to find the moles of HCl in this problem statement?
Yeah.
We do, because we have a volume and a molarity. Molarity is moles per liter. Times that by this turned into liters, you have moles. We also have the same thing for sodium hydroxide. When you have information to find moles of 2 or more reactants, that is a limiting reactant problem. And I know it says it, but I like to go with it. When you do limiting reactant problems, you always find moles of each one. I'm going to do my HCl first. I have 0.0250, well, technically there's another 0 there, liters. My molarity is 0.151. I break molarity up into 0.151 moles of HCl. Per 1 liter of solution. We can find moles of HCl. We'll do the same thing for sodium hydroxide. I get 0.003775 moles of HCl. Zero point 0.001151 moles of NaOH.
Where's the, what is it? Bulk solution.
Sorry, say that again?
1 liter.
Oh, this says 1 liter of solution. Sorry about that. 1 liter of solution. It's just me breaking the molarity into moles per liter so I can cancel my units.
Same.
Yeah, I apologize. Okay, so Monday people, you've seen this before. Wednesday people, you will see it today. In this particular problem, all the coefficients are 1s. And in limiting reactant problems, you typically take the moles of HCl and you find out how many moles of product you can make. And then the smaller amount of moles it helps you determine the limiting reactant. Okay? Here, everything is 1 to 1 to 1 to 1. So if I were to ask you how many moles of sodium chloride you could make from this many moles of HCl, you would say that exact number. If I was to say, how many moles of sodium chloride can I make from this many moles of sodium hydroxide, you would say this exact number. Are you comfortable with that? Well, you will be by the end of the day. Questions about that? Who would like to see it? Nothing on my sleeve, except arm. Do you believe me? That's a better question. How many people believe me? I'll take it. All right. So, because what I'm about to say is that because this is the smaller number of moles, this is the limiting reactant. Next, if this is the limiting reactant, how many moles of HCl, or how many moles of HCl will react with this many moles of sodium hydroxide?
0.00151 moles HCl.
The exact same number of moles. 0.001151 moles of HCl, 1 to 1 coefficients will react with this. So we'll call that moles of HCl reacted away. And then when I put a minus sign here, and then I subtract my moles of HCl start with moles of HCl reacted away, and I get my moles of HCl left over. I'll then ask if there are any questions about that number. If not, let's check in and see. The question says, what is the pH? Do we have pH yet? No. Some would say we're not even close. But we're getting closer. The next step is to solve for the concentration of HCl, which will be equal to the moles of HCl left over. Divided by the total. Question, Leo?
Why did it go to 2 sig figs for moles HCl left over?
Oh, sorry. Because I skipped. Thank you. I skipped the 6 and the 2 in the middle. 0.002624. Fix that in minutes, because that's what you. Thank you. So all I'm going to do is I'm going to write the number of moles left over here. My total volume is the sum of the volumes that I've mixed together. So these two volumes are the volumes of my HCl and my sodium hydroxide solutions that I've mixed together. And I'm left with 0.0719 molarity or molar HCl. Now, this molarity has to be lower than the molarity that I started with because I reacted away some of my HCl. Good. Once I have a molarity of HCl, I know that's equal to my molarity of H+, and I can plug that into the pH equation. So now we're back to this problem. My molarity of hydrogen ion, H+, is 0.0719, and I can find the pH of that. And I get a pH of 1.3. Question?
So you're finding, so this question is asking what's the pH of
The mixture.
the leftover excess reactant?
Yep.
Something has,
Because everything else turns to water.
Everything else, so this many moles of HCl and all my moles of sodium hydroxide became water and sodium chloride. So yeah, they're reacted away. It's a neutralization reaction, right? It's like the culmination of everything we've done so far. It's a double replacement neutralization reaction. It's a limiting reactant problem, and you have to solve for pH. Let me take a quick look over here at your old exam. There's got to be at least one of these on here somewhere. That's odd. Oh, there it is. Good. All right, so it's coming up. It's a really nice problem. Yes.
Are you going to give us problems with different ratios? Will it be?
Am I going to give you problems with different ratios? Can I just hedge my bets here and say no? There'll be one-to-one stoichiometry. Turns out that there's only one strong acid that has two H's. It's sulfuric acid. When you have sulfuric acid and you react away the first one, you get a weak acid, and things get too complicated.
You mentioned that it's two reactions, right?
Yep. Sulfuric really is made up of two different reactions.
And it doesn't lose both of its hydrogen atoms, just one for every molecule, right?
Right. Let's just say sulfuric acid, because it has involvement with a weak acid. A weak acid is a person or an acid of interest, and so we don't go there. But that's why. Could be nitric acid here. Could be perchloric acid. It could be any one of the strong acids that is monoprotic with one H+. Could be sodium, potassium, lithium, rubidium, cesium hydroxide. Well, if you check the notes, there's another one coming. That says 21.51 milliliters. That's a companion problem. 31 milliliters. That should be a companion. No, that's the next one we're going to do. Oh. My apologies. The rest of them are companion problems. So there's 31, 41, and now we're going to talk about titration. Titration, a technique used to determine the concentration of an unknown chemical through quantitative addition of one reactant to another. In Chem 400, we do acid-base titrations. There are other titrations. There are redox titrations. We don't do them. We do acid-base titrations. I only mention this because titration is a general technique. Quantitative means with very precise numbers. Qualitative means very few numbers. So we're being very quantitative. Now, the definition of the equivalence point for a titration, the point at which stoichiometric amounts of acid and base have been added together. As we will see in discussion this week, at the equivalence point, both the acid and the base are limiting reactants. The end point. The end point is when a property, let's say this, when a physical property of the solution changes. And as an example of what I mean by that, there's this thing called phenolphthalein. It is a pH indicator. At pHs less than 8.2, phenolphthalein is colorless. At pH is greater than 8.2, it is pink. And not just any pink, it is a deep, deep pink. It's beautiful to behold. Anybody ever do a titration involving phenolphthalein? Yeah. It's good. Now, it turns out that for the equivalence point of an acid-base titration involving a strong acid and a strong base, the pH will be 7.
Page what?
pH will be 7. So if you do hydrochloric plus sodium hydroxide, at the equivalence point, the pH is 7.00.
So the specific ratio of the two mixed together.
Meaning, right, when we have the moles are the same, which is what our stoichiometric amounts are, and they are both the limiting reactant, the pH will be 7.00. And perhaps what you're noticing is that the color change for a phenolphthalein solution occurs at a pH of 8.2. Those are not the same. But between a pH of 7 and a pH of 8.2 is approximately a quarter of a drop of the sodium hydroxide. Have you ever put a quarter of a drop into anything? It's hard to do. I'm not going to say it's impossible. Like, well, take a drop and then with a knife cut it into 4 pieces and then put one of those in. So here's what the point of so many points going on. So even though the end point, like the end point is meant to be the same as the equivalence point, what I'm telling you is that between pH of 8.2 and pH of 7, pH of 7 is perfect. pH 8.2, there's a quarter of a drop, which is close enough. And that's why the end point is when a solution, a physical property of the solution changes. It signals the equivalence point, but it is not the same thing. So, signals the equivalence point. But it is not the equivalence point. They can be very different. And so, my job as your instructor is when you do the titrations lab later in the semester, I will choose the indicator. Sometimes it'll be phenolphthalein, sometimes it'll be other indicators, such that you are talking about the equivalence point. So we don't have to think about it too much. But that's the difference between the equivalence point and end point. Equivalence point, moles equals moles, stoichiometrically. End point, we figured things out, so it works out nicely. Anyway, any questions about that? Okay. Let's see. Next slide. We'll catch up. There we go. Has everybody looked at the lab schedule? Do you know which lab is the titrations lab? It's lab 8, so we have like 8 weeks before we do it. What is the material for the exam is on this exam? Pictures of a titration. This one, the entire solution is colorless. The indicator is phenolphthalein. Got my favorite construction, that PHTH construction, so it sounds like you're going phenolphthalein. But just pronounced as interestingly, as if the pH is silent. That's a chemistry joke in there somewhere. Phenolphthalein. All right, so if it's colorless, what does that mean? That means that the pH is below 8.2. Functionally, it means that the solution is acidic. When I say functionally it's acidic solution, it's because between 7 and 8.2, there's a quarter of a drop. So colorless will be acidic.
There are flowers that change color if you water them or put them in the vase. Acidic or base.
Definitely. Cabbage, purple cabbage. You ever make an indicator out of purple cabbage? Or so if you don't like the color of your purple cabbage, put it in a vase. It'll turn blue.
And you can eat it.
Depends on the base. Short answer is no. All right. Entire solution is pink. pH greater than 8.2. I'm sorry, I can't write just one decimal place for these. I'm going back into altering it. There we go. All pHs have 2 decimal places. Functionally it's basic, and truly it's basic. Can you see a little bit of pink swirl in here? Do you think this is acidic or basic?
Oh.
This is what's called a non-equilibrium situation because it hasn't entirely mixed. This could go entirely pink. This could go entirely colorless. When you do pH titrations, if you see 2 different colors, or colorless and a color, it means mix it to figure out which one of these it is. So this one is, we can call it not mixed. And the word that we'll develop over this and next semester is called equilibrium. It's not at equilibrium. And another way of saying is it's not stable, it's not final. So hard to tell for this one. But this, we will see this, and you'll always have to mix it to get one of these. Now I won't be able to get a quarter of a drop. You're going to do drops, right? When you do this in lab. And so in one drop, the perfect titration goes from completely colorless to a faint pink, or some color pink for the next
Phenolphthalein.
What's that? Phenolphthalein. It's as if the pH in the middle of the word is silence. Yeah, we should have time. The titration of 10.00 milliliters of HCl solution of unknown concentration requires 12.54 milliliters of 0.100 molar sodium hydroxide solution to reach the endpoint. What is the concentration of the unknown HCl solution? This is very similar to what we'll do in lab. We need the reaction for this. We've written this, I think, 3 or 4 times already. It's a very common reaction we do in Chemistry 400. Hydrochloric acid plus sodium hydroxide goes to water plus sodium chloride. Now, our process is this. We observe the color change, which is the end point.
It's not balanced. Oh, it is now. Sorry.
the end point is assumed to be the equivalence point. Like I said, we don't have to think about it too much, but they are within about a quarter of a drop of each other, so close enough. The other thing we said was that at the equivalence point, both the acid and the base are limiting reactants. Another way of saying that is moles of acid equals moles of base. And another way of saying that is that you can use, since they both reacted equally, you can use the stoichiometric factors. And that's what I'm about to do. I have 12.54 milliliters. That's 0.01254 liters of, which always means multiply, 0.100 molar sodium hydroxide. Break that into moles of sodium hydroxide per liter of solution. Because they're both limiting reactants, because moles of one equals moles of another, however you think about it. I can use the 1-to-1 mole ratio based on their coefficients, which are both 1s, to convert to moles of HCl. Sure enough, I get 0.001254 moles of HCl. And now that I have moles of HCl, I can calculate my concentration. Now when I'm writing this up, I'm writing that the concentration of hydrochloric acid is the moles of hydrochloric acid over the initial volume of hydrochloric acid. That's because in one of the previous problems that I did, I had total volume down here. I am trying to find the concentration in this problem before I mix them together. On the discussion this week, we were always trying to find the concentration of the mixture after we add them together. Maddie?
Get a different answer for moles of HCl.
What'd you get for moles of HCl?
0.001254.
Let's see. This is 0.01. If I times it by 0.1, I should have an extra 0. Good. I've been known to add extra zeros myself. All right, so now I'm just going to write my moles. I'm going to write my volume, which was 10 milliliters. I'm going to solve for the concentration, and I will be done. And we will be out of time. And as they say, time is what turns kittens into kittens. That is the end. There's one more companion problem at the end, and we are finished with the material on your first exam. We will start Chapter 5 on Wednesday. Your review time is not part of lecture time. Happy to talk about any of the things such as old exams, homework 4, anything else you want to talk about. And I guess the last thing I will say is Lab 3. Lab 3 is next week. Lab 3 has 8 safety templates to do. Those are all on the Chem 400 website. So have those
Have a sheet each.
on one safety template each. Could be multiples on the same sheet in your notebook, though, however you work that out. I should be able to see them all, though. I don't want you to stack them. And the Wednesday lab from 8 to noon. You cannot take the exam next Wednesday unless you come and do the lab. Because that's the rules. I don't know. So you cannot skip lab to study for the exam is what I'm saying. Not that anybody would do that, I know, but it has been enunciated, and so I will keep track of it. That's it.
You said you can start chapter 5.